Alrighty, so I'll be presenting Roblox Cube, which is Roblox foundational 3D intelligence model. So first off, kind of what I'll be going over in the presentation is just the background of like previous papers on 3D mesh generation in different ways and different implementations that people had, and then just the overview of Roblox Cube, and then I'll be going to the encoder-decoder architecture, how they actually train the encoder-decoder. What are some applications to the model? What's next? And then if people want to stick around for some math part, I tried my best to explain phase modulated positional encoding, which is something you'll see in the paper later on. So just some knowledge that people should probably have, and I can go over anything real quick if people don't, is just how LLMs work. Basically, you don't need to know inner workings of anything, but how you have self-attention mechanisms, multimodality, how they are able to take in other types of information, 3D meshes and point clouds. So as you can see in the photo there, point cloud is just a collection of 3D points representing an object. So if you think about it, if you just had like a text file and you had, XYZ, 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 collection of that, that's what a point cloud is. Voxel, that was just included in the image, but that's not really necessary for this. But think voxel as like Minecraft, like if you're building something in Minecraft. And then a polygon mesh is a collection of triangle faces and vertices. So basically, that .obj file, which is what Roblox Cube uses to, or what their file format is of choice for creating meshes, just a text representation where it'll say, V, and it'll have XYZ, or if it'll have F, and it'll say, like, the size of the face. So just think that's polygon meshes are all objects in video games, basically, unless you're in Minecraft. Anything with high resolution or detail is going to be a polygon mesh, just a collection of a bunch of triangles making an object. And so now on to the first set of previous work. So I actually presented a paper on this along with Jacob a couple years ago now. So when we said that was sophomore year, beginning of sophomore year, so 2 years ago. This isn't the exact paper. This is a more recent paper. But the way people used to make 3D meshes or generate 3D meshes is you would have text, and then you would use some sort of 2D diffusion model, and you would render multiple views of that same image. So in the example here, it says a cute dragon. So, or you can use images, and then you render multiple views of that image, and then through some other methods, then you extract a point cloud from that, and then you just convert the point cloud to a mesh, and now you have your mesh. So that's obviously it's not as good as what I'll show you in this using transformers, but it was pretty easy. It just used diffusion. You ran diffusion a couple times, extracted the point cloud from it, and now you have a mesh. The problem is you obviously can't control you can't control the entire 3D object. If you just tell a diffusion model, show me the right view, left view, you're kind of leaving it up to chance. So it's not super accurate, but it worked decently well. The other big problem is that it's unable to interact with outside systems like large language models. There's no way to use 3D shapes. You would have to take a photo of a 3D shape, and then you're just back to 2D. So there's no real 3D understanding or knowledge. You're just generating 3D meshes. And then some people also tried just using regular large language models like GPT or Claude, or what do they use in this? Llama. And you just generate those object files that I was talking about before, so you can kind of see, if you see my mouse here. Yep. So you see how there's the vertices and then the faces, I think, at the bottom. Yeah, so there's faces and vertices. So you would just tell the large language model, generate me a 3D OBJ file of a bench or of a barrel or of whatever. And it could do it all right. This here, it's actually not the best. It could understand shapes all right, but the big problem is you're just leaving it up to whatever its training data is. You're not actually, again, involving any 3D intelligence. There's no intelligence in this model. It's just using previous object files it's seen and spitting out new ones. It doesn't really understand what an object is and how shapes combine to create an object. People for this just fine-tune different LLMs, and used a bunch of in-context learning. So you would just give it a bunch of examples, a bunch of images, and a bunch of OBJ files for those images, and that was all the training that was done. So obviously, this isn't going to be that great. It's a similar architecture to fine-tune coding models, but obviously there's a lot more code on the internet than there is object files with text descriptions of those object files. The latest thing, this was released a couple weeks ago. I tried it myself on my computer. If you just download Claude, you can use Model Context Protocol, which was released by Anthropic. It's just like a, what's the word for it? Like just a program to interact with, to use a Claude to interact with other outside software on your computer using different APIs and such. So this actually worked pretty well. So let me see if I can. There we go. So this is like a quick GIF. I sped it up because it was a really long video. But basically, you would open up Blender, which is a 3D, what's the word I'm looking for? I don't know. Some sort of 3D rendering or 3D creation software. And then you just tell it, hey, create, in this case, a low poly example of a cabin in the woods, and it gives it an image. And then it just, everything in Blender is Python files. So it just knows from its training how to create Blender files, and that's the extent of its knowledge, and it just goes in and does that. It's actually pretty well, but what you need to do is you need to refine it with a lot of examples, descriptions, and kind of, it's not super quick to create a 3D, a good 3D model. You have to really sit there for a couple hours. You also have to know the terms. You have to know what you're talking about. So it's not good for beginners. You have to probably know Blender, which is already complicated software in itself, and then you have to know how to give a 3D artist description of a scene. So it's decent if you know how to do all that, but it's still, again, not truly understanding 3D space. It's just spitting out files that work. So now on to Roblox Cube. So this is Roblox start of what they call a foundational model for 3D intelligence. Think how GPT-4, Llama 405B, or Claude 3 is a foundational model for large language models. This is similar for that, but instead of understanding text and understanding language, it understands 3D space. Just I'm on the same thing. Okay. So in their paper at the beginning, they line out detail out three pillars that they required to consider this a true 3D foundational model, which is learning jointly from sparse multimodal data. Basically, there's not a lot of 3D data available on the internet, especially with any sort of descriptions. So it has to be able to work with just regular meshes, which I talked about before, but also layouts of scenes, has to be able to take in textures, rigging, program scripts, and then CSG is constructive, something geometry. I'm blanking on the whole term, but basically think CSG is just using basic shapes, using spheres, cubes, cones, anything like that to build a model. So it's obviously going to look kind of like how Roblox, if anyone knows what Roblox looks like, any of the games, they usually use CSG modeling. And then it has to also be able to handle unbounded input-output size through an autoregressive model, basically the same way that you can, obviously with token limits of like 120K for GPT, but you can input as much, and we're relating it to LLMs, input as much text and get out as much text as you need. This needs to be able to do the same with 3D models. You need to be able to give it as complicated or as big of a 3D model as you can take, and then spit out whatever you need to spit out as detailed as you need it. And it also needs to be able to collaborate with other people and AI systems through these multimodal inputs and outputs. So again, this is just their start for a 3D intelligence model because it can't do all of this to the greatest degree. I'll go over like the training data that they use, but it's just using 3D meshes. It doesn't use any other types of training data, so it's not learning from all these different types of data that they said it needs to be able to learn from. And also, they don't have unlimited detail in their models. You'll see later, it takes 1,000 or 8,192 points from a 3D mesh, and that's what it uses. So that's what they lined out as the start for something to truly mean to be a 3D intelligence model. They also moved away from previous diffusion and those large language model techniques, so whether that's interacting with Blender, generating the object files or using diffusion, and wanted to move towards actual spatial understanding and have a model that understands what 3D space is. And so this is an example of some of the outputs that you can get with their model. So here's you can either input either way, and you'll say a unicorn with a rainbow mane and tail, and it'll spit out that mesh, or you can give it that mesh and ask it for a description, and it'll spit out that description. It works both ways. So going into the overall architecture of the model, what they do is instead of using text tokens like a large language model would, they use shape tokens to understand 3D space. So as you think of a token represents a word, like one token represents and, one token represents the word this. You have discrete shape tokens which represent different shapes in space. Obviously, we know basic shapes, but their code book was, I think, a little over 16,000 different discrete shape tokens is what they use to represent space. If I remember correctly, GPT-4o has about 200,000 tokens to represent text, but they also can do a bunch of languages, so that it's kind of if you want to compare the two. And then they want to be able to decode those shape tokens into meshes so the model works either way. So some applications of it, which I'll go over after I explain the actual tokenization architecture, is you can input text, you can get text tokens, and then using text to shape GPTs or shape to text GPTs, you can go either way. Generate shape tokens in mesh or mesh shape tokens, text. And then they also have another application which is text to scene generation, so that's kind of taking that a step further. If someone says, hey, I want this scene and details out the scene in text, they want to be able to create a scene layout, so that's also still in text using a JSON format. And then you split each section of the scene, so each object in the scene, into different text descriptions, and then using that same architecture above, you create those shape tokens and in turn generate that mesh and then put it all together to the scene afterwards. Yep.
How do you go from the text input to the scene layout again?
So I have a slide on that at the end.
No worries.
Okay. All right. And then, yes.
Yeah, so for the tokenization of shapes, like shapes exist in a continuous space, right? You can have like infinitely many shapes that look very similar. So how exactly does it like discretize shapes into tokens? Because what if there's like a curve that looks slightly different or slightly modified to another curve? Does it have like basis shapes?
So that's one problem I did have with this model, and at the end I kind of say like what I would like to see next, and that is a larger codebook for shapes, because you are forcing the model to use specific tokens, even though, because you could think if you get really detailed, you can just get to a small plane, and then if you just put a bunch of small planes together, you can build a mesh or something like that. But the model uses 512 tokens to represent a mesh, which I don't feel is enough to represent a detailed mesh, which is why when you see in most of the examples, even if you look in the input mesh here and the decoded mesh there, it takes anything that's detailed and turns it into kind of a low poly rendering of that. So I have the same question, which is why not have a larger code book to represent more deep, complicated shapes? Yep.
You say it uses 512 tokens to represent mesh. What does that mean?
So that's actually right into the next thing, which is the encoder-decoder architecture. So I'll explain that through this slide. So again, we're just walking through this, taking an input mesh, tokenizing it, detokenizing it into a mesh. And like I said, just like LLMs use tokens to represent text, Cube uses tokens that represent geometry. So this is the model architecture. So we're going to walk through kind of each step piece by piece and understand how it works. So we start with that input mesh, which is those faces and vertices. And then we sample from, when they're sampling it for the encoder, they're sampling points from the surface of the mesh. So if they normalize everything into a -1 to 1 bounding box, so if you think in 3D space, you have -1 to 1 to x, -1 to 1 on the y, -1 to 1 on the z, everything's normalized to that, and then they sample 8,192 3D points from that mesh that are on the mesh. They don't sample random points that aren't on the mesh. Like if, say, in the top corner of the box there's empty space, they're not going to sample that. And then they run it through phase modulated positional encoding, which is a big term, And I'll explain that in the next slide. But basically, you have with regular transformers, you have to encode the position of, or not regular transformers, but regular LLMs. If you want to encode a sentence, you have to know where in the sentence each word is. And then you just use regular sinusoidal positional encoding to do that. I explain the math at the end if anybody wants to look into the math. But also if you want to just look up regular sinusoidal position encoding yourself, you can look at that math. But basically, think you have a vector representing a token, and then you want to move it just a little bit so that so that you're encoding the position of that token in the space it's in. So in text, you want to encode, the first word, and make sure the model knows that came first. When it comes to points, you want to make sure you want to know where points are in relation to other points, because you can't, just like if you have a large paragraph, if you have one word at the beginning of the paragraph, it doesn't really need to know what the last word of that paragraph is. They're not going to be super related to each other. It's going to be more like if you break it up into a sentence or the words on either side of it. Just like, but if you do that with a point cloud, if you go, I only care about the points around a certain point, it's hard to understand the global structure of the mesh. You're only going to understand, or the model's only going to understand specific fine detail areas, and it's not going to have an idea of the entire point cloud. So what phase modulated positional encoding does is it combines regular positional encoding, which can get fine details, and their phase modulated stuff, which again I'll go over, and it can understand both fine and coarse details of the mesh. Now we take those, so if we have those 8,192 3D coordinates, there's 128 frequencies that they evaluate each of those points on, and it's not each one of those points, each one of the scalars in the points. So now we have a 3 by 8,192 by 128 tensor. That's what the mesh is encoded into. And then we put that through cross attention, and if you know anything about visual transformers, it's just taking these learnable queries, which are a set of vectors which are trained, and you apply cross attention to them. So it's and then you take that. Let me see if I didn't. Okay. You take that output from the cross attention. So those learnable queries, I'll go over in the next slide. You apply self attention. So that's regular transformer stuff if you understand transformers. And now you apply here. They apply self attention 12 times. And now you have 512 continuous latent vectors. So you just have, they use the word continuous here because it's not discrete tokens. But Jinan and I, when we were going over the paper, it's confusing wording, because if you say continuous, you don't think there's an end to the vector. You would think that it's just going on forever. But it's actually each, what would it be? In each dimension is continuous, where it's not assigned a specific number as when you have the tokens from the code book. And then, let me see. So another thing they introduced in this paper, or not introduced in this paper, but they take from another paper, which is Dino V2, which is Meta's vision transformer, is latent space regularization with self-supervised loss. Again, another big term, but I go into this as well afterwards. It's basically training the model to understand the similarities between meshes, or dissimilarities if they're very different meshes, and it's just a training feature that enhances the model's accuracy when you're using it for those later applications. And then they apply, for when you have those 512 vectors that have been taken from the transformer, the cross-attention and self-attention, they apply optimal transport vector quantization, another big term. Jinan will also present a slide on that, because that's what his, what is it, the next 2 weeks?
Next week.
Yeah, his reading group on the next 2 weeks is actually about this same stuff, not specifically optimal transport vector quantization, but it is optimal transport?
Yeah.
Okay. And basically think that just turns those 512 continuous vectors into, let me see, 512 discrete shape tokens. So we have those 16,000 shape tokens that have been defined, or that are trained through the training process when you're training the encoder-decoder. Optimal transport vector quantization takes that and takes the output from the encoder and is able to make it into discrete shape tokens. So in this case, each, oh, yes?
To does that convert each token into a discrete, each vector into a discrete shape token?
Yeah, so 512 vectors, 512 tokens. Or, Janin, is that true? If you have the 512 individual vectors, is that each vector corresponding to one token, or is that not how optimal transport works?
Yeah, each
Okay.
each token or each vector corresponds to some token within the code.
Okay. So yes. Another piece they introduced to the training architecture is stochastic gradient shortcut. So this is something that has been applied in other vision transformer models, and at least from what they lay out in the paper, they're not really sure why adding their linear layer before works, but it does. So instead of taking the continuous latent vectors and transforming them all into shape tokens every time during training, that can sometimes introduce a local minima when you're training the code book, and you want each token. You don't want, basically when you're training the code book, you don't want the tokens to just get stuck where they are. You want to make sure that throughout the entire training process, you're looking at the actual continuous latent vectors and making tokens that represent the most repeatable ones. So when you take when you're training 50% of the time, instead of transforming those vectors into shape tokens, you just straight up send the vectors to the self-attention of the decoder part. But what Roblox does is they actually introduce a linear layer here, which nobody's done before, and that introduces just an extra set of weights. And let me see if I have my notes on this here. That must be on another slide. Yes. So I'll talk about more about the stochastic gradient shortcut when I go into how they train the model. This is just kind of the architecture overview. And now we're just back into, okay, so here's the actual codebook size. And now we're just decoding it, so you're doing it in reverse. You're applying self-attention and then cross-attention. So the way to do cross-attention when you're decoding a mesh is like I stated before, each mesh is bounded or clamped to -1 to 1 through 3D space. So what you want to do is you want to sample. They sample half. Oh no, that's for the training. Sorry. So they just sample uniformly. I don't know what detail they go to. I couldn't find that in the paper, but just know from -1 to 1 in the X, Y, and Z space, they sample 8,192 points. And that's just points in space. Apply the phase modulated positional encoding again. Now and then you apply cross attention. And what this does, what they've trained it to do now, is you create an occupancy field. And this is just some complicated computer graphic stuff, which isn't too important to know here, but just an occupancy field is you'll just have those 3D, you'll have the points in 3D space, and each point is assigned a probability of it being part of the mesh or not. So obviously in here, this is a 2D representation of it. I think I say that, yes. The red spots would mean there's a high probability it's part of the mesh, and the blue spots mean there's a low probability it's part of the mesh. So we're training the decoder to generate this occupancy field, and then it's an algorithm called marching cubes, and then they also use quadric errors and then some post-processing to turn that occupancy field into a decoded mesh, and the post-processing stuff kind of cleans up the mesh if there's any weird leftover spots. If, for some reason a random point was decided it's part of the mesh in the occupancy field, that takes that out. If you want to look it up yourself, you can just look up marching cubes. It's like a 1990s algorithm that was used for computer graphics. I didn't look too much into it. I just know that it's able to decode that occupancy field into a mesh. So that's the overall architecture. It's really complicated. I'll go into each section specifically. So I'll go into the phase modulated positional encoding, and then I'll go into the latent space regularization with self-supervised loss, the stochastic gradient shortcut, and then Janine will go into the optimal transport vector quantization. Yes?
For the marching cubes, does it work I'm just confused how it can go from 2D to 3D.
So that's a 2D. So I'm saying specifically in this slide, that's a 2D representation. But when you have it's a 3D vector when you're looking the occupancy field is created. Does that make sense? So they're saying through XYZ space the probability that each point is in.
Oh, I see.
Yeah.
They're just visualizing here.
They're visualizing it in 2D.
reality,
It's a 3D
okay,
object. Yes. Yes.
We went from like the positional encoding has 128 dimensions, and then we went down to 32 for the shape tokens. I got a little confused there. Is it just the transform block that we're just reducing the dimension?
I believe so. They mentioned once, let me pull it up here, in the paper what the architecture is for those transformer blocks.
I'm presuming it's the first KV correction.
Then you're losing all the information.
So they said we use similar transformer layers for both the for both the encoder and decoder, with each layer having 768 width and 12 heads. The encoder and decoder consist of 13 and 24 transformer layers, respectively.
So then I have another question. How are we going? How are we going from 512? So the 512 vectors, each of them have
32 dimensions.
Okay, yes. How do we go to 32 dimensions from 768 width?
I'm not sure. They don't detail
Okay.
further in that what's specifically in each of the transformer blocks. That good? Okay. Moving on. So I'm going to explain the phase modulated positional encoding. So that's, again, the first part here once we take that point cloud. This is the first step. The motivation behind this is, like I said, sinusoidal positional encoding works well for language, but not in 3D space. In language, we know that one word doesn't really influence a word 200 away from it. It's not that important to it. But in space, that can be very important. So we need to capture both the coarse and fine details in space and add the two together, basically. So what they propose is taking the original positional encoding, which is, let me use the mouse here. That's this on the left. So if you're looking here, the input, -1 to 1 in 3D space, this could be the X, Y, or Z, whatever, and the 128 frequencies we looked at. Objects that are near each other are, would it be represented with different values? You know they're different from each other because one word to the next, or they're close to each other, sorry. One word is close to the next word, if that's what you were thinking in like large language models here. And then the let me read this real quick, sorry. Yes, and then we go to the phase modulated, which instead of which takes the original positional encoding, which is an exponential, which has an exponential component to the formula. Again, the math's at the end if anybody is interested in looking over it. But as you can see here towards the end, when we look at the 128th frequency, everything is very similar to each other, which you don't want in 3D space. You don't want to just assume that every point away from another point doesn't really matter. And then, so we use the phase modulated section, which is just it's hard to explain these graphs, which is why the math's at the end. But as you can see here, it's exponential. Here, it's slowly getting bigger. So you're basically saying how the attention mechanisms are relying on the dot product between the two position vectors to measure how similar 2 points are. And in regular positional encoding, it'll say they're very different if they're far away from each other. But in 3D space, we don't want that. We want to have we want to be able to represent what 2 points that are far away from each other, how they're interacting with each other. It's complicated math, so I even have a hard time understanding it. But it's able to encode 3D objects much better than just regular positional encoding is able to encode 3D objects, because it's regularly used for language. And now, Jinan, you want to talk about?
Okay. Yeah. So I probably need the board. Is it okay if I do this up first and that? Okay. There are two major components here, right? Optimal transport and vector quantization. In order to actually understand this, we have to go in the reverse direction. So let us first understand what vector quantization is doing. If we go back to the graph over here, right, we have this entire kind of right portion where we are going from continuous latent vectors to discrete shape tokens, and we need to understand what's inherently happening here. For a second, let's consider like a toy example. So in just 2 dimensions, right? I have xy plane, and this is R of 2, correct? And there are infinite points that exist within this plane, so this is a continuous space. Now, the idea behind discretization is that I will just chunk it into separate components. So, like that, and you have one here, 2 here, and then so on and so forth. You can explicitly see that you have X number of possible options or buckets that you can put your values into. Now, the idea or the reasoning behind why we're actually doing this process, rather than just considering a normal encoder-decoder process, like a normal encoder-decoder architecture, we would simply just take the latents and try to decode those latents, correct? In this case, we are performing this discretization step because of, like this is a theorem in information theory that basically suggests that using discretization allows for better reconstruction because you do, slight modulations in the latent vectors basically get accumulated into the same shape token at the end of the day. So the resultant value that you get does not change if the continuous output of your encoder model is over here or anywhere within this region basically. So that's the main reason we're performing discretization. Now we can talk about optimal transport. The problem with the vanilla optimal transport, or vanilla quantization scheme that you use, basically the vanilla scheme is just cosine similarity. You just find whatever is the most similar bucket, and you just put the latent vector within this bucket. Now, what happens a lot of the time is that the range of the latent vectors is relatively small, so a lot of encodings kind of just end up within this tiny little box. And a consequence of that is that the code book, right, which is effectively just like the embedding layer, or like the word embedding layer but for shapes, gets overloaded, where a lot of representations are basically just tied to one specific code book, or like one specific code. So if we look at the graph over here, we can see that as you increase the size of your code book, the utilization of the code book also reduces, because everything just clusters to the small set of tokens that have close cosine similarity, so whichever just comes in within the bucket, and that is a problem. So what you do is you impose a constraint. You say that every single code token can only have one value, so only one value can map to a specific bucket. And that basically gives you a much more complicated optimization problem, and that is solved using optimal transport. So instead of all of them going to the same thing, which is what is nearest, it goes, each of them gets assigned the most efficient route, basically, where each piece of data, each latent vector is corresponded to some value within the book. And the consequence of that is, I kind of drew this out again, I guess, but it's kind of the same thing that is happening where instead of bucketing every single token or every single code is assigned a specific token, and the consequence of that is that the entirety of the code book is utilized, even when you have 16,000 tokens. So you basically recover a lot of reconstruction error, because before you were only using a very small percentage of the token. Now you're able to actually you're utilizing a very small percentage of the code book. Now you're utilizing the entire code book. As a consequence, you are able to reconstruct the original 3D model much more efficiently. So that's the idea behind quantization, vector quantization, which actually allows us to go down to 2 from positive infinity, presumably, and from here to point 8 is where optimal transport happens. So those are the 2 main things. The details regarding math for optimal transport we'll cover over the next 2 weeks. Alright, I guess it won't come back up, or wrong one? Sorry. There you go. Back to you.
So, I have a question.
I have a question, yeah. So what if multiple vectors are supposed to be like put into the same thing?
Yes, okay, yeah, very, very nice question. So, the important thing about the codebook is that it is learned, right? Which means that it is initialized from completely random, and once you complete that initialization process, it is learned through the process of training. So, if 2 latent vectors are very similar to each other, the code that is learned, right, the embedding that is learned is just going to be similar at the end. So you basically lose nothing from using optimal transport, because if you do require clustering where a lot of them have the same code, you will basically learn that anyways, right? But in this case, you are restricting that expressivity because you come in with that inductive bias of most of the shapes are going to use that same discrete representation or the same embedding. But with optimal transport, you basically rid that bias, and if it is the same, it will learn it anyways. If it is different, it learns something different. And it turns out that learning something different is actually necessary, because if it was a futile effort, then the reconstruction loss would probably remain high. But now we have seen that it actually goes down pretty significantly. So it is a meaningful addition. More questions? Alright, awesome.
Sweet. All right, so just looking back at the encoder decoder architecture, so now we've learned how the phase modulated positional encoding, what it is, not really how it works. How it works is at the end if you want to see that. And then normal attention, we're going to go into the learnable queries section next, and how it is able to turn into discrete tokens. So now we want to, well, I messed up my animations on the slides. But if we want to know the encoder, how to actually train the encoder and decoder, which I kind of just took snippets, little crops of the original diagram. We take that input mesh, just like before. Sample is 8,192 points. Now we have a point cloud. And then we apply the phase modulated positional encoding to those individual points. So now that we have vectors. And then we apply the cross-attention and self-attention layers, along with the learnable queries is after, but we'll apply the cross-system self-attention. Make sure I'm on the same page here. Okay. Then we apply the optimal transport vector quantization so that we can actually get individual tokens. Apply the decoder. 50% of the time we apply that stochastic gradient shortcut, which, like I said before, stochastic gradient shortcut just passes those latent vectors that the decoder creates, that the last self-attention layer or self-attention block generates. It passes those through one linear layer directly to the decoder. Just as this is a snippet from their paper, just so you can kind of get the intuition behind it. I kind of said it before, but they said, our intuition is that the additional linear layer, which is something they came up with, nobody's done this linear layer on the stochastic gradient shortcut before, in our formulation allows the shortcut pathway to learn a slightly different set of weights, but with well-defined gradients. And it allows the shortcut pathway to act as a teacher network for the quantization pathway. So basically, this stochastic gradient shortcut is going to help be basically a teacher to the optimal transport vector quantization. And as a result, the quantization pathway is less prone to being stuck in a local minima. So let me see if I can. Yes?
How can you backprop through optimal vector transport?
That would be a Jin question.
We will discuss this next.
Okay, because I did not see that you could backprop.
No, it's a very, very good question. It is an optimization problem inherently, right? So it is difficult to inherently backprop through it, but there are algorithms. One is sync-horn algorithm that allows you to differentiate through orbital transport.
And then what is, I don't really get why not, like, I just use the raw outputs of the encoder, throw away the linear layer they're using, and use them as a decoder. Because I see where they're coming from, because like you can basically like that, like what I'm seeing is like you're basically saying like, okay, like the optimal vector transfer should give you basically something similar as the output of the encoder block, right?
Yes. But it can get stuck in that local minimum, like it said. So if I'm trying to think.
Well, like how would like the local, where would the local minimum actually happen?
So my guess is if I could represent this visually, if I can go back to his slide. So you see like this section here, how you, or whatever, broken into, what is that, 5 different parts, right? If you're only most of the time, but not all of the time, using...
We're not using that one though, we're using the one below.
Oh, yes. If, okay, well that kind of breaks my analogy, but I was going to say if you're most of the time only using a subset of the tokens, with optimal transport, you would end up with most of the tokens what would it be in that local minima area. It would be in that region around it, if you're thinking about it like space. And you don't want tokens to get stuck all being generated in that space. Does that make sense? A little bit?
Kind of, yeah. It's good.
Okay.
Yeah.
Let me see if there's anything from their paper that kind of gives it better.
I'll probably just like look into it as well. It
Okay.
does not make any sense. Like I get that there could be problems with the local minnow, but I don't get that just like throwing a cap. Did they do any activations on top of it? Or is it just a linear layer, no activations?
They said one linear layer. I don't know the stochastic gradient shortcut, like what the standard is for that.
Yeah, I guess maybe it would have been like, okay, I'm sorry.
Oh, good.
Yeah.
Yeah, I'm not sure. So then once we apply that decoder, we generate that occupancy grid like I talked about before. We take the ground truth, which is the input mesh, and calculate the loss. Now the ground truth here, obviously we can't take the mesh. We do have to take a point cloud from it, but it's not the same point cloud that is applied to the encoder, because we want to not only learn what space is filled, we want to learn what space is not filled. So when we're sampling the points for the encoder, it's all points from the surface of the mesh. But when we generate that occupancy grid, we want to train the decoder to be correct in empty space and filled space. So we take half of our 8,192 points and sample them uniformly throughout that negative 1-to-1 3D space. And then we sample the other half from the surface of the mesh, just as we would for the encoder. So they just split it half and half, and that makes the decoder much better at being able to be accurate in the negative space and the positive space. Calculate that loss, back propagation through the entire encoder-decoder network. Anybody have questions on the training section of it? I don't know if I have a slide specifically on their training data. Since it is Roblox, they have access to a lot of training data, a lot of objects that people have just opted in for training on their platform. If you ever like make a model on there, that's in there. Yep.
Is inside the mesh, like within the volume, considered empty, or?
No, that would be filled space. Yeah. Which is why, like, I specifically said, like, the 2D representation, or the occupancy grid before was just a 2D representation of what an occupancy grid would look like, because it is 3D. It is all the points from that negative 1-to-1 3D space. And then they also used a data set called, I think, Objectiverse, I think was the name of it. Again, just public data set with a bunch of 3D meshes, and it had descriptions on top of it, which they applied later for the GPT section of it, like the text to shape and shape to text GPTs. And then they just took all those meshes and then applied this training architecture to it. No questions on that? Perfect. Okay, so now we're going into that latent space regularization with self-supervised loss. So let me spam the keys a bunch here. Back here in that training only section, where's the mouse? Up here. So this is a thing that was taken from, let me see here. Oh. I'm on the wrong page. I'm using two computers here. Perfect. Okay, so this was taken from Dyno V2, which is Meta's vision transformer model, and this is an extra training step to the encoder that is able to. I have some images so you can actually understand it visually, but it's basically able to better understand what similar models are look like. So it's just able to make a better encoder. So what you do is you take these learnable queries, which is just a set of vectors. They don't define in the paper how big this is. And now you have a student encoder and a teacher encoder. So same thing as before, you take that input mesh, the point cloud, apply the phase modulated positional encoding. Now you have vectors that can go into the student and teacher encoder. And then from those student and teacher encoders, you apply the cross attention, self attention. Now you get those latent vectors. And now this is trained on top. So now this is new stuff, is this MLP head. So you just put an MLP head at the top of both the student and teacher encoder. And Janin, we were not able to determine if it was a scalar or a vector, right? This p-value?
Scalar is what we landed on.
Okay, yeah, that's what I wrote down. So we landed on, we think this p-value is just a scalar. They don't put it in, they don't say it in the paper, and then we looked in the Dyno V2 paper. They don't say it in the Dyno V2 paper. So we're assuming we're just putting out one score, a 0 to 1 score after this MLP head. Apply cross entropy loss. Obviously a stop gradient on the teacher encoder because we don't want to we don't want to do back propagation through the teacher encoder. We just want to do back propagation through the student encoder. And we use exponential moving average of the student encoder to create the teacher encoder. Anybody have any questions on this? Luckily, this architecture is not as complicated. Yeah.
Yes, like my first question is, what is P of S here? What are you trying to actually predict? Like the basically whatever you max
S is student, T is teacher, but
yeah, but what is P and like what's the task exactly here?
that's what we tried to find out. We couldn't figure out what this p-value is supposed to represent. Just a value of 0 through 1 is what we landed on.
There was no semantic intuition that we got for this. The idea is that it is self-supervised, which means that the encoders are basically the teacher encoder is teaching the student encoder to reconstruct
And just be robust to basically
to
looking at different parts of your image.
Just be better at encoding.
Just be more robust.
Yeah.
Right? It's like basically you're saying that okay, using only like a max portion of my information, I should
still be able to get a similar match.
Similar results. That's why I think the P is the same.
Yeah, it's exactly. So that's what
We just want those values to be.
But there's no real semantic interpretation of what P of S should be.
Also, why are you using P of T log P of S? Why is it not P of S log P of T?
P of T is the label. P of T is the teacher, right?
Right, but then why don't you see the KL divergence?
Well, the internal entropy, the K divergence, the first term is intrinsic entropy, which is PT log PT, and that is not affecting the optimization because we have a stop gradient through the bottom half. Right?
Oh, it's just it won't work.
It won't optimize it. It will. You can use K divergence, but you're just computing an external.
They're the same thing. Like P and Q here are basically the same thing.
Yeah.
Right?
Yeah.
Okay. Was I supposed to have an hour, or how long are these supposed to go?
Hour. Yeah.
Okay, so I'll speed up here towards the end. So this is just the results. On the left is without this self-supervised section on the encoder, and the right is with. As you can see, it's still able, obviously, it doesn't change how well it's able to recreate one mesh from another, but it's able to understand what similar meshes are to each other. So here, you have the car, and you have a tree, or you have a car in a box, and it's just, or you have a car in a different type of car. They should be very similar. So this is obviously, I guess it would be like a dot product of how similar these two things are. And this car and this car should be very similar meshes, but it doesn't understand that because it's not trained without this student and teacher. When you train it with that, you're able to have the model have a better understanding of what similar objects are to each other in 3D. So as you can see here, obviously the car is at least similar to a tree, and then an ice cream cone, and then 3 other cars, or 2 other cars in itself. That's that. This is just another version of that. Or this is a different section about encoder training. Ground truth, this is obviously just the models that were passed into the architecture. KL is continuous latence. That's if you don't use the code book. So obviously you'll get more detail, but you get more detail passing the continuous latence directly into the encoder. But the problem with that is now you don't have tokens, and without shape tokens, you lose any access to plug and play with other models. You don't have a text to shape GPT, you don't have a shape to text GPT. So while you lose some detail creating the shape tokens, you're able to enhance the capabilities of the actual model itself. And then Craftsman is another model throughout the paper that they compare all the results with. So this is obviously its old thing, not that great. Okay, so now to the applications. I'll go through these quickly because it's not too much here. For the text-to-shape and shape-to-text GPTs, or no, just text-to-shape, it's a decoder-only GPT-2 style model where it just decodes text into shape tokens. The way they generated the training data for this is they rendered multiple 2D views of a model. So you take a model, you spin it around on all the 3 different axes, and then you just pass a couple of those images into GPT-4o, and you actually just ask it for description. So they're not using human labeled data here. You're just assuming that GPT-4o, their 2D or their image understanding is good enough to be able to create descriptions for this. They for every object they create 3 different types of descriptions: a short description, which is this here, just that's one simple sentence. A medium one, which is maybe 2 to 3 sentences, and a long description, which is about a paragraph, going into like a lot of detail about what the model looks like. The way they do it, they take the text prompts, encode using clip, dual stream attention for the text and the shapes, and then transformer and shape tokens. That makes sense to everybody? Perfect. Now you have shape to text. You do the other way around. You input a 3D mesh, tokenize its shapes. Now you have discrete shape tokens, and then what they do is they just do a latent projection using an MLP to turn it into data that can work for their LLM, which they fine-tuned, obviously, on these outputs. They use intern VL 2.52b. Never heard of that LLM before. I don't know why they chose it specifically, but they did.
Lava?
What?
Lava? L-A-V-A?
LLM intern VM.
Oh, it's just a fine-tuned. I think it's just.
Yeah, next token prediction loss is a Lava thing. That's like something they came up with. That's why I just put that there if you want to look it up yourself. And now from that 3D mesh, you've now generated a text caption. The training, like I said, it's the same data set as the previous one. It's just in reverse now. Instead of giving it descriptions and asking for meshes, just do the other way around. Meshes ask for descriptions. Here, there's a funny thing. I think I told Janine about it, but if anybody else can notice a funny thing about when they do the shape to text and then back the text to shape, does anybody notice something weird about those models? Low poly.
They look like Roblox models.
There you go. This is a says futuristic humanoid robot. It just says the head is small and integrated in the body. It doesn't say anything about the head, but obviously you see the training data in action here. It gives it a Roblox head. That's just a standard. If you know anything about Roblox, that's just a standard Roblox head. So it's kind of funny. You see, because it's not a large model in terms of, it's not like 400 billion parameters or anything like that. You see the training data in action sometimes, and you are right about it loses a lot of detail, which is like what I was saying with the encoder training. Obviously, when you use the vector quantization to get the code token or the tokens from the code book, you lose a lot of detail because there's way more complexity than just 16,384, I think it is, shapes.
So does this mean that one or some of the tokens make up the Roblox head in the tokens the shape tokens that we use?
I don't know if it would. I think it means more that when they were training the LLM with the 1.5 million objects, so many of those had the Roblox head that when its idea of a head is a Roblox head. So what it thinks a head means is just a Roblox head in 3D space. Okay. Scene generation analysis. So this is their last application. You give it a prompt. You say, in this case, an anime Japanese pagoda. I don't know how to say that scene. Now you just use a normal large language model, whatever you want to use. And you the way they fine tune it is they just use in context training. So they just give it in the prompt a bunch of examples of scene generation. And you generate this JSON data at the bottom here. So here it says scene 1, object category. And so each object is going to have an object category and a description, position, how big it is in the scene, and its rotation in the scene. So you have just a normal large language model, which is good enough at being able to say, like, hey, a table's here, and then if you want a computer, the computer's going to be on top of the table. It knows enough about that to generate the captions and so on. And then for each object in this list, you use their text-to-shape model, generate those 3D models. Everything's textured using Roblox's texture model. I forget the name of it, but that's another paper that they published, is generating textures based off of 3D meshes and descriptions. And then you use the position, extent, and rotation to arrange the objects in whatever engine you would want it. And now you have a scene. Like I said, the training is just in-context learning with some prompt and scene examples. What's next? Roblox says what's next is they want constructive solid geometry. That's what the word I was looking for earlier. Is be able to have the model use that, which is just saying, I want a sphere here, I want a cube here, I want a cone here, blah, 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 and to create meshes instead of using vertices and faces. 4D generation, so that's the next step, is they want to, whatever that fourth dimension is, whether that's rigging the model for animation, creating those actual animations themselves, scripted motions, programming for those models, etc. They want to be able to add that to it. They want to enhance multimodality. They want to add images and videos. They say images are coming soon, which I assume is just, I don't know if the LLM they used for the text-to-shape or I guess the text-to-shape, so they train that themselves as GPT-2 style. However, they add images to that. They want to add multimodality, so you can actually, I assume that would probably make a much better or much more accurate mesh to what you were originally looking for. Some things I'd like to see, most of it's just making the model bigger. I just feel like it's not enough. Larger data set, they only use 1.5 million objects. That's not nearly enough, as we see with LLMs just eating up all the text on the internet, to just now kind of get to a point where they really have a good understanding of text and language. To be able to get that for 3D, we're going to need a lot of data. Human-made descriptions, I just don't, it works, but just using AI to create training data for AI, which can kind of give itself a little feedback loop if it is a widespread thing, just scares me a little bit. Larger codebook, GPT-4o, like I said, has 200K tokens. Cube only has 16,384. Feel like that's not enough to represent space. More tokens per mesh. This is why every single mesh looks low poly and turns out low poly, because you're only using 512 of these tokens. You're only using, if you think about each token as a shape as you would each LLM token is a word, you're only getting 512 shapes to create an entire mesh. That's obviously not good enough for detailed meshes. It's okay for low poly. I'd like to see integration with those Blender MCP tools, like I was showing earlier with Claude and Blender. If you can, integrate, it's kind of similar to like the scene generation. If you can integrate Cube into, you have Claude use Cube to generate some meshes, and you import those meshes to Blender, and then Claude moves those meshes around in Blender to create a scene. I think that'd be cool. And then luckily, kind of just as regular LLM and multimodal research advances, Cube should be able to take advantage of anything, just as they took advantage of the optimal transport vector quantization and the latent space regularization stuff from Dino v2. They should be able to take advantage of all that. And I think that is, that's all. The math is afterwards, but I know I'm like 10 minutes over. So any questions overall on the whole thing? Yes.
Yeah, is the 512 limit, is that due to just it would take too long, or you don't have enough computing power? Or
That's my guess. I have a 4080 Super at home in my desktop, and it took to create a model to the same, the same degree as these. Because the code is all out there. It's just on GitHub. It's nothing closed source. It took, if I remember correctly, it was taking like I feel like it'd take like an hour or two to create one of the, like I just leave it running overnight, and it'd take an hour or two to create one of the meshes, and it used 100% of my computer. Like I couldn't even open a tab or anything. Like it would crash my computer while I was running it. So I assume if they're wanting, since it's Roblox, they want it to be integrated in their engine. So I assume they want it to be fast and quick whenever people want to make stuff. They don't want people just waiting an hour or two to get meshes. So I assume that's probably part of it. And that's actually probably the only real explanation, because other than that, you could just make the model bigger if you wanted to. Yep.
I thought it was a data constraint because they don't have enough data to like scale it up. Because like if you increase the actual embedding size, like you increase your vocabulary, you do that to like capture more relationships in your data, right? So
Yeah, there's not enough relationships to understand. Is that what you're saying? Yeah, that makes sense. That's a good explanation. I didn't think of that.
So is that also why you have token limits on like regular, not regular, but just normal like ChatGPT or
like to like generation limits?
yeah.
That's just like, are you saying like context window limits?
Yeah,
or like
the content.
well, context window you have limits because like you increase your complexity, right? Positional encoding, you can't capture like past like. I mean, standard positional encoding can't do more than like basically 4,000 tokens, but everything else like they just like hack it together to like 120,000 tokens context.
Also, attention is expensive. Like
Yeah.
computing
Yeah.
attention, it scales with some.
Well, I mean, no, you have a KB cache. You're caching it, so every single new token is OBAN operations.
Yeah, but it scales as you increase.
Oh
the
yes,
context window.
yes, but
That makes it slower.
yeah.
So something like Gemini, which has 1 million token output window, I think.
They're using a different. They're using the Titans, right? Titans or
I don't know.
Mamba.
I don't think. No, Gemini's proper transformer architecture. Right?
Just
I think
I
so.
don't know. I don't know if
They
they
use
can
a
scale.
different attention.
I don't think. Yeah, I don't know if they can scale.
But like in-house in Google, could they make that output window 5 million tokens? If they're like,
I mean,
Just want as much compute power. You're saying just throw as much on it.
yeah.
I'm not sure.
Okay.
Not sure.
ask Google.
It's a good question, but they don't publish their papers, so I don't think we can give a definite answer.
We cope.
Yeah, we cope.
Any other questions? I know it's really complicated and a lot of stuff. Let me go back to just the overall architecture. Questions? Nope. All right.